Okay, I think I have calmed my dog down enough. Nope, haven't. Okay, you know what? She's not going to calm down. UPS is here. And if you want to see this tonight, just, I'm sorry, deal with my dog barking. All right, so, anyway, this is going to take a little bit longer, not just because of my stupid dog, but it's good than the other guy because I'm going to give a little bit more detail. So maybe if you're not in calculus, you didn't fully understand him. I'm not, okay, calculus picky people, I'm not going to really worry about form or anything else. I just want you to have the idea. This isn't probably something you'll have to do on the mechanics test. This is going to be something that's more like it's a lead-in to really important topics in E&M, just kind of like today when we talked about sigma. I'm sorry, this is supposed to show which way this is spinning around the axis. This is like going counterclockwise. So this is going to be really important in like a week or two. This is like a great lead-in. Also, if you were in my class last year and you did the Calder, the mobile lab, and you know how I like wouldn't let you find the mass of anything like with a balance or scale, I just made you find volume and use density and guess what material it was made out of, especially the rod that it went on. This is why. This is a lead-in. So basically I tortured like 200 people for 30 of y'all. So feel lucky, I guess. Or whatever, just but it should help you. So if you think back to that, if you remember that at all and what a pain in the butt it was, that's why. So let's talk about this. Let's pretend this is what I was doing earlier because, yeah, just because. You know those nasty Slim Jim things that are like beef jerky but not, they're all greasy? Let's pretend this is one of those. And someone stuck like a, shish kebab skewer through it and skewer, however you say it. And it's going to spin around the center. That's its axis. This is its axis of rotation, as the guy with the weird hair would say. So what I want to do is let's first define the whole length of this, as I'm going to go for capital L here, so I'm going to be like the other guy. Okay, so that means that this chunk of it from here to here would be half of L, so L over 2, as would this one. So, half plus half, whole. There's another way you can kind of define this. Let's call each portion R. And what that is that just is, I was saying it's because it's like rotten and nasty to like a few of you I explained it to today. Basically, let me be a little bit more clear on that. That is like what that is from the axis of rotation out to the end of rotation. So if you had just like something else, your R would be like, let's say I just had like a stick spinning, or I'd put the little barbecue skewer over here, then the whole thing would be your R. But just for this, we're going to say R. So what we can say definitively right here is that R, as I've said right here, will be the equivalent of L over 2, the entire length divided by 2 in this case. Okay, I need to be really clear. This is a very specific Slim Jim spinning on a toothpick thingy around the middle. Okay, so I want to show you the other thing. Okay, let's also say that we're just assuming that this is a line of particles, which it kind of is, but we're going to ignore any kind of volumetric tendencies and just call this linear, this little skinny pepperoni jerky stick. So what you would use is linear density. So it's mass over length. So this would just be the mass of the entire jerky stick over the length of the entire jerky stick. And we're kind of making an assumption that it's pretty consistent because, hey, they grind up all that nasty stuff pretty fine. Anyway, sorry if you like Slim Jims. So we'll come back to that. Now, let's go to the equation for moment of inertia. Now, oh no, calculus alert, deal with it. It's really easy. I'll explain. All right, so that's going to equal this. Now, you can call this the integrand that tells you that you will need to find the antiderivative, or as that one lady put, the underivative, or, the area under the curve of the graph, or you can call it an evil snake. I might call it an evil snake because, non-calculus people, it's evil, kind of looks snaky. All right, and let me give you the equation for this. It's going to be r squared. Guess what your r is? This from here to here, the rotation to the end. Okay, times little d, like this is the curvy tiny d, times change in mass. All right, you can put that in parentheses or not. My little tablet thing's acting weird, so I'm just going to leave that like that. All right, let's define this little r. Okay, I don't think you can see that color. Let me do this in yellow. Okay. So let's say that you slice this thing up into just this one side. Let's make just this. We're talking about this side right here. Let's say you slice this up into really little pepperonis for a little mini pizza because, you know, you're putting nasty little Slim Jim pepperonis on something. So you slice up the whole thing like ridiculously thin, like pepperonis, like with one of those deli slicer thingies. I don't know. Anyway, so you have just a whole bunch of these like really tiny little, I guess pepperonis would be more not yellow, hopefully. Just really tiny like little things that, you know, you can, if you stack those up, like think about it, if this is like the top view, like if you're looking down, I guess if you cut them, like if you put them on a piece, you know what pepperonis look like. Anyway, so, and if you stack them, just think about this, you can stack those up for some reason, or you could kind of stack them back on here. So imagine what would it look like if you just took this one side and sliced it, left this one here on its little toothpick thingy, sliced it, right? And then you started slowly stacking them back on, okay? So you can kind of vary the length of this side. Stay with me on this. I swear it will be important for Gauss's law in electrostatics. All right. So that's kind of the visual I wanted you to have. That's kind of what I was talking about today in class. So let's call this just one of these nasty little pepperoni slices. Let's say that that is a tiny change in, let's say little r, just because, you know, like we're cutting r up. So let's say tiny little r. That's just, hopefully that makes sense to you. We're making this r small. We're cutting it into little chunks. That says dr. All right. Now let's go back up here. You know what? You can solve this thing for mass. Right here in red, let's look at this as the overall like consistency of the entire stick, like the linear density of a Slim Jim officially or whatever. This is the big important part of this concept. That's kind of like the general density thing. Well, you can kind of express this another way and make it a little bit where it kind of follows the same form. And it's going to involve this, but it's a little bit more specific. So let's look at this. Let's rearrange this first for mass. So we would have mass, and you know what? Let's make that like this really tiny change, since I'm doing this in the pepperoni color. That really tiny mass, like the mass of each one of these stupid little slices, if it stays there. So tiny change in mass. And that's going to equal, so we're just going to rearrange that. So let's say that's like D. Okay, so do that. So that would give you lambda, your linear density. All right. Times, and let's not use L. Let's use, because, you know, I guess the thickness, whatever you want to call it, would be dr. Hey, look, see this? That's right here. You can substitute this in right there, because think about this as a function. What is your overall r, or r squared, equal to? Like right here. What is this a function of? What does this depend on? Well, yeah, it depends on your mass, but let's look it up here. If we're stacking those pepperonis back on, how long this is, and thus how long, or you know, what the value of this squared would be, this r, would be how many of those pepperonis you put back. So it's a function pretty much of how much of these little slices you put back on. Kind of weird. Does make more sense with the charge. Anyway, so let's look at what that would be. So therefore, moment of inertia for a Slim Jim spun about the center axis would be integral. This is the area under the curve, or the slope if we decide to have the slope of this, or just, you know, adding up all these little pepperonis, r squared, right? And then I'm going to substitute this over here in for your dm. So that would be lambda, tiny change in how far. You know, that's basically dr, thickness of little pepperoni. Okay, so now you see this lambda up here. You can take this general consistency of all the extra leftover pink slime stuff on the floor that they put together for this, and you can put it in right here. Because, see, that's like your lambda. Your lambda is kind of your overall linear density. And that will work out because you're slicing this so thin. Just think of it like you could pick up one of these and examine it, and overall the density would work out to be this because you're taking the whole mass over the whole length of the Slim Jim. So we're going to do that. So therefore, moment of inertia is evil snake. Sorry, calculus people, I can't help it. It's funny to me. All right, this r up here, squared. And then we're going to go, let's go mass over length. See, for your lambda, I'm putting in this m over l, the mass, total mass over total length, dr. Change in, you know, Well, that's just your pepperoni slice. You get it, hopefully. All right, now, first let's look at what's consistent like what's constant, what's not going to change. Well, since they've ground it all up so finely, all of the little extra parts, I'm thinking your density is going to be pretty consistent. All right. Change in R. Yeah, you did slice these up like the same, but this always, you need to have this change thing on this side. This is, yeah, you didn't slice these up any differently, but this D, anytime you have D like change in, it really does. This is a calculus thing. I'm so sorry if you're not calculus, just kind of go with this. It needs to be on this side of the integrin, aka evil snake thing. Okay, so, but the only thing that you can really take out of this, because, yeah, it's not going to change, it's going to come out here, is the ML. And this is going to be mass over length, or your lambda. Mass over length, and that's going to be R squared D. I'm going to put this in parentheses because this is a function of dr. And that's the other reason it needs to stay over here, is that this R squared, remember, like I said, it depends on how many pepperonis you stack back out. That's a function of that. You're not going to need to graph this. I mean, maybe. No. This is just all very strange to do, but it's a good lead-in for what we're going to do soon. So you have that. Now we're looking at this. You've seen this maybe, 0, which 0 would be where this spins up here. And the end of it, I mean, would have to be at L over 2, because that's all the pepperoni food products that you would have. So 0 L over 2. And let me talk about that in just a second. So quick reminder, because this could be the part that people forgot, I'm going to do this in a different color, that derivative and antiderivative, or integral, antiderivative, underivative, whatever. I'm going to teach you for the power rule, which is all you need to know, a trick I figured out for how to remember what to do on antiderivative. Okay, because see how this is? We got ML, and you might have to, I'll go over this in class tomorrow too. Okay, so you got that, and then you got R. I'm just kind of recopying this because I'm about to do something with it. It's easier to do up here. Okay, so you have all of that. Now, what you would do with this, think of antiderivative AD. What you're going to do is you're going to add 1 to your exponent up here, and then you're going to divide all of this term by that number that you get. So for this, so let me give you an example. So if you wanted like, if I wanted to do this procedure to smiley face to the 5th, I would add 1 up here first, add antiderivative, add 1 to your exponent. Okay, and then that would be 6, right? So I'd have smiley face to the 6th, and then I would divide it by 6. All of that divided by 6. 6. Smiley face to the 6 divided by 6 in this case. All right, so let me scratch that out. So over here, let's look at what we would do. So therefore, and yeah, calculus people, not going to do this right at all, just writing it, okay? Just I'm going to write it out. I'm not going to solve it with proper form. You don't have to. Mass over length, okay? And that's going to be, let's derive, go ahead and figure out what this is. Okay, so that would be 2. I'll do this in a different color. This will go, okay, 2. See, I'm going to do plus 1. I'm going to add 1 to my exponent. That's 3, and then so this whole thing's going to be over 3. So we're going to do this, and that's going to be, this right here is going to be R to the 3rd over 3. And you see how we have this? You'll see like a line sometimes that has like a 0 and an L over 2, but I'm just going to tell you, we're going to take this, L2, as far out as this can go, and we're going to plug it in right there. Normally you would plug that in right there, and then you'd plug whatever number in is down here in, and then you would add them or subtract them depending on whatever you're trying to accomplish. But since this is 0, we don't have to worry. So we're just going to plug this in right here, because this R can only be how big? It can only go out to the length of L over 2. So therefore, inertia would be mass over length, and then if we plug this in, it's going to be, I'm just going to do this as kind of scratch work over here. That'd be L cubed, and then 2 cubed, which would be L cubed, and then 2 times 2 is 4 times 2, that would be 8. So L cubed over 8. And so we'd go over here. That becomes L cubed. And then I'm leaving my 3, and then I'm putting this with 8. Hopefully you see where I got that. Anyway, and then I'm going to bring that down here and just multiply it times m over L. So you would have L cubed over 24. And there you have ml squared over 24, 1/24 ml squared. And when I saw that, when I worked this out this morning, I was like, oh no, that's not right, because it should be, I will tell you this right now, the moment of inertia of a slim gem spun around the center should be 1/12 ml squared. What I had done wrong, hopefully you see, is I'd forgotten we had a whole other side over here, because think about it, they're both spinning. So you really need to like double this in this case since you have 2 identical sides. So that's how you prove that the moment of inertia using linear density is for a thin rod spun about the center is 1/12 mass times the length of the whole thing to the second power. And check out your units, kilograms, meter squared. That works for moment of inertia. So hopefully this helped. I'll go over in class tomorrow.